Okay, in this video, we're going to be looking at probabilities and how probabilities are determined. This begins chapter 9, which deals with probability, and in this section 9-1, we're going to be determining probabilities. We're going to be looking at mutually exclusive events, also complementary events, and non-mutually exclusive events. We need to begin with some definitions that are related to probability. One of them is experiment. An experiment is an activity whose results can be observed and recorded. A couple of examples would be tossing a fair coin would be an experiment because we can observe that activity and we can record either heads or tails. Also, tossing a fair die is another example of a experiment because we can roll a die and find out what number comes up on that die. Okay, the next definition is an outcome, and that's each of the possible results of an experiment. So again, when you toss a pair of coins, you're going to have two outcomes, heads or tails. And then for rolling a fair die, a single fair die, you're going to get one of six outcomes, 1, 2, 3, 4, 5, and 6, or 6. Then next is a sample space. That's the set of all possible outcomes for an experiment. Of course, the sample space, when you toss a pair of coin, the only two outcomes will be heads or tails, which represents the sample space. And also a fair die. The outcomes are 1, 2, 3, 4, 5, and 6. Okay, that's another example of a sample space. And then the event is going to be any subset of a sample space. Okay, let's look at this example 9-1. Suppose an experiment consists of drawing one slip of paper from a jar containing 12 slips of paper, each with a different month of the year written on it. And you want to find each of the following. Okay, here you want to find the sample space, which is capital S, for that experiment. So here the sample space, by definition, was the set of all possible outcomes for that experiment. Okay, and by the way, the experiment was drawing a slip of paper from a jar that contains 12 slips of paper. So in this case here, we have to list all 12 months of the year from January through December. Okay, that represents the sample space. Okay, then the next example would be an event A consisting of outcomes having a month beginning with J. In this case, the event A, that event, of course, is a subset of the entire sample space. In this case here, it will be January, June, and July, because those months begin with the letter J. And by the way, that's an illustration of an example of an event, which is a subset of the sample space. Another example of an event would be event B, consisting of outcomes having the name of the month that has exactly 4 letters. And there are only 2 months that fit that particular situation, and that's June and July. June has 4 letters, so does July. Okay, so that's another example of an event which is a subset of a sample space. And the event C consists of outcomes having a month that begins with M or N. In this case here, there are 2 months that begin with the letter M, that's March and May. And the letter N, there's only 1 month, November. So this represents the event C that consists of outcomes having the month that begins with either the letter M or the letter N. Okay, now let's look at how we can determine probabilities. Okay, now there's a couple of types of probabilities here. One of them is the experimental probability or empirical probability. That's determined by observing outcomes of the experiments. So in other words, if we toss a fair coin, let's say 100 times, and we want to count how many times we get heads after the 100 tosses, that would be an experimental or empirical probability. Also, theoretical probability is the outcome under ideal conditions. So if I toss a fair coin, then the probability of getting heads theoretically would be 1/2. Or the probability of getting tails theoretically would be 1/2 as well. Or rolling a fair die, the probability of getting a 1, I would say, would be 1 out of 6. Next is equally likely, is when one outcome is as likely as another. So if I roll a fair die, I would expect to get A. Each number will have a fair chance of coming up on will have a fair chance of being shown when you roll the die. So 1, 2, 3, 4, 5, and 6 will each have a fair chance on equally likely outcome, because the probability for each one of those will be 1 out of 6. And a uniform sample space is each possible outcome of the sample space is equally likely. Okay. The law of large numbers, or Bernoulli's theorem, is this. If an experiment is repeated a large number of times, the experimental or empirical probability of a particular outcome approaches a fixed number as the number of repetitions increases. So if I roll a fair die, toss a fair coin 500 times, then that particular probability, or the number of times that I roll a fair die, should be close enough, or should be the same as the probability of tossing a fair coin. Of course, or of getting heads would be 1/2. That is, if I want to record how many times I get heads after 500 tosses. That probability, or that number of heads, should be the same as should be close to the probability of obtaining the heads on a fair coin. Okay, let's look at the probability of an event with equally likely outcomes. For an experiment with sample space S with equally likely outcomes, the probability of an event A is this. Now here we write this as P with the A in the parentheses. That means the probability of event A, that's going to be the number of elements of A divided by the number of elements of S, which can be abbreviated as lowercase n sub A divided by capital N sub S. Okay. Let's look at this example here. Let S equal to 1, 2, 3, 4, 5, and so on up to 25. If a number is chosen at random, that is, with the same chance of being drawn as all the other numbers in the set, calculate each of the following probabilities. Part A is this, the event A, that an even number is drawn. Okay? There are 25 numbers from 1 to 25, so these are the numbers that can be drawn that are even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which means that there are 12 even numbers out of 25. So the probability of event A would be the number of elements in A, which is 12, divided by the number of elements in the sample space. That's 25. So it's 12 over 25. Part B, the event B that a number less than 10 and greater than 20 is drawn. Okay. In this case, event B is going to be the empty set, because we have to look at numbers less than 10 and greater than 20. Now, and means the intersection of the two. So that means in this case here, that intersection would be the empty set. Okay, so there are no numbers that are less than 10 and greater than 20. That's the key word right there, and. So that means that the number of elements in B is going to be 0. So that means that the probability of event B happening will be 0 over 25, or just 0. And then part C, the event C, that a number less than 26 is drawn. Well, you have 25 numbers from 1 through 25, and they're all less than 26. So that means that probability for event C will be 25 out of 25. So 25 over 25 will be simply 1. Okay. Now these two examples here, B and C, have a certain name, certain type of event. Well, we'll get to that a little bit later. Part D is this the event D that a prime number is drawn. Okay, now these are the list of prime numbers that are less than 25. In this case, 2, 3, 5, 7, 11, 13, 17, 19, and 23. And there are 9 prime numbers from 1 to 25. So the probability of event D would be 9 over 25. Okay. And part E, the event E that a number both even and prime is drawn. Well, the only even number that's prime is the number 2. Okay? So that means there's only one prime number. There's only one number that's both even and prime. So the probability of event E occurring would be 1 over 25. Okay, now remember parts C, well, actually B and C that I went over? Well, the probability of the event B that a number drawn less than 10 and greater than 20 is 0 over 25. That's called an impossible event. That's an event with no outcomes, and that probability is 0. And also the event C, that a number less than 26 is drawn, that's a certain event, because the probability there is 1. Okay? So here, if the probability is 0, that's an impossible event. If your probability is exactly equal to 1, then that means you have a certain event. Okay, and let's look at some probability theorems here. If A is any event and S is the sample space, then the probability of event A is always going to be a value between 0 and 1, and that does include 0 and 1. In other words, your probability cannot be less than 0, and the probability cannot be greater than 1. So here the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. All right, let's look at this example here. If we draw a card at random from an ordinary deck of playing cards, what is the probability that A, the card is an ace? Okay, in a deck of playing cards, there are 52 cards in the deck, of which 4 of them are aces. So that probability of drawing an ace would be 4 out of 52. And we can reduce 4 over 52 in simplest form by dividing the numerator and the denominator by 4 to get 1 over 13. So the probability of drawing an ace will be 1 over 13. Okay, part B, what is the probability that the card is an ace or a queen? Okay, so in the deck of 52 cards, 4 of them are aces, 4 are queens. So if we add those two, you're going to get 8. So the probability of an ace or a queen would be 8 over 52. 8 over 52 can be reduced by dividing the numerator and the denominator by 4 to get 2 over 13. So the probability of drawing an ace or a queen would be 2 over 13. All right, now let's look at mutually exclusive events. Events A and B are mutually exclusive if they have no elements in common. In other words, the intersection of events A and B must be the empty set. In other words, events A and event B have nothing in common for those two. Like, for example, let's consider one spin of the wheel. Here in this case, the sample space is, of course, all 8 numbers, well, all 9 numbers from 0, well, all 10 numbers, from 0 to 9. A is event A, is going to be the 0, 1, 2, 3, 4, and B is going to be these numbers, 5 and 7. In this case here, A and B are mutually exclusive events because, in this case here, A and B have nothing in common. So if event A occurs, then event B cannot occur. And that's the restriction for a mutually exclusive event. Okay, so if events A and B are mutually exclusive, then the probability of A or B is going to be this notation, the probability of A, the union of A and B, which is going to be the sum of the two probabilities, the probability of event A plus the probability of event B. So in other words, the probability of the union of events such that any two events are mutually exclusive is the sum of the probabilities of those individual events. Next, we'll look at complementary events. Two mutually exclusive events whose union is the sample space are complementary events. Like, for example, consider the event A, which is going to be 2, 4, of tossing a 2 or 4 on a standard die. Then the complement of A, and the notation for the complement of A will be A with a bar on top. That means the complement of A would be these numbers 1, 3, 5, and 6. Because the sample space, of course, is 1, 2, 3, 4, 5, and 6. So in this case here, if we have A being 2, 4, then the complement would be the remaining numbers 1, 3, 5, and 6. And in this case, the probability of event A would be 2 over 6. Because you have two numbers out of 6, then the probability of A complement would be 4 out of 6. In other words, you subtract 1 minus 2, 6 to get 4 over 6. Okay, and here, if A is an event and A bar is its complement, then the probability of A plus the probability of A complement would be equal to 1. Okay, and then the probability of A complement would be equal to 1 minus the probability of A, or we can say the probability of A would be equal to 1 minus the probability of A complement. Okay, now we need to look at non-mutually exclusive events. That means that the two events have something in common. We're going to let E be the event of spinning an even number. In this case, E in this case will be 2, 4, and 18. Here we have a wheel with numbers on it. And 2, 4, and 18 are your only even numbers there on the wheel. So there's 2, this is 14, there's 18. And we're going to let T be the event of spinning a multiple of 7, which is, of course, 7, 14, and 21. Okay, now these are non-mutually exclusive events because if you look at event E and event T, what's in common is the number 14. Okay, 14 is in both of these events. So here the probability of the union of E and T would be the number of elements of the union of E and T divided by the number in the sample space. That's going to be equal to the probability of E plus the probability of T minus its intersection of E and T. Okay, now while we subtract this off because we want to avoid double counting. Okay, because we got 3/8 here and 3/8 here, but we're counting the number 14 twice. To avoid that double counting, we have to subtract off the intersection of those two. So that's why you see minus the probability of the intersection of E and T. So in this case here, the probability of event E is going to be 3 out of 8 numbers. So that's 3 over 8. The probability of event T would be 3 over 8 as well. So you got 3/8 plus 3/8. Then you have to subtract off the number of items that are in common in both E and T. There's only one number that's common in both E and T, and that's the number 14. So that's why you see minus 1/8. So if you do 3/8, 3/8 minus 1/8, you'll get 5 over 8. So the probability of E or T happening would be 5/8. Okay, so here with non-mutually exclusive events, you have to do the subtracting of the probability that gives you the double counting, or what's in common in both. Okay, we'll summarize the probability properties. Number one, the probability of the empty set is 0, which is an impossible event. The probability of the sample space is always equal to 1, where S is the sample space. That's called a certain event. And then number 3, for any event, the probability of event A is always going to be a value between 0 and 1. And that does include 0 and 1. So keep in mind, the probabilities cannot be negative and it cannot be a value bigger than 1. It's always a number that's less than or equal to 0, well, greater than or equal to 0, and less than or equal to 1. Then number 4, if A and B are events and the intersection of A and B is the empty set, that means that A and B have nothing in common, then the probability of A or B, or you can say the probability of the union of A and B, will be the sum of the probability of event A and the probability of event B. Then number 5, if A and B are any events, then the probability of the union of A and B, A or B, would be the probability of A plus the probability of B, and then you have to subtract off the intersection of the probability of the intersection of A and B. And that's for non-mutually exclusive events. Number 4 is for mutually exclusive events. And then number 6, if A is an event, then the probability of the complement of A would be 1 minus the probability of event A. Okay, that's for the complementary events. Okay, look at example 9-4. A golf bag contains 2 red tees, 4 blue tees, and 5 white tees. In part A, what is the probability of event R that a tee drawn at random is red? In this case, the bag contains a total of 11 tees. In this case, you add the 2, the 4, and the 5 together, you're going to get a total of 11 tees in that bag. But 2 of them are red. So the probability of event R, that's the probability of drawing a red tee out of the bag, would be 2 out of 11. Okay, so it's 2 11ths for the probability of drawing a red tee. Part B, what is the probability of the event not R? That is, drawing a tee at random that is not red. Well, that represents R, the complement of R. So the probability of R complement, or the complement of R, will be 1 minus the probability of R. So in this case, the probability of not drawing a red T would be 1 minus the probability of drawing a red T. Well, we found out that drawing a red T would give us a probability of 2 over 11. So 1 minus 2 over 11, and you have to think of 1 whole as 11 over 11 because the denominator is 11. So 11 over 11 minus 2 11s will be 9 11ths. Then part C, what is the probability of the event that a T drawn at random is either red or blue? That is the probability of R union B, red or blue. Well, red and blue have nothing in common, so we look at this. We take the sum of the probability of a red T and the probability of getting a blue T. Well, for a red T, we found out it was 2 over 11. So that probability of drawing a red T is 2 11ths. The probability of drawing a blue T, there are 4 blue T's out of 11. So that's 4 over 11. So we just simply add 2 11ths and 4 11ths to get 6 11ths. Okay, so the probability of drawing a red or a blue T will be 6 over 11. Okay, and that will conclude this particular video on section 9-1 on how we can determine probabilities.